Good morning, everybody. It's Scott here. Thanks so much for attending this morning's webinar. We're going to be covering ratios. We appreciate you guys all coming, as always. Key to solving Gmat math problems, one really important key, and I say this every week, and I'll continue to say it for those of you who are new, is you got to find ways to make things simple. Because in the world, on the Gmat, we have innumerable opportunities to make things more complex, okay? And those of us who make things more complex are always going to struggle over those of us who try and make things simple. And I'm not saying it's easy, but we should at least try, right? It should be our goal to make things simple. Almost every Gmat math problem will give you the ability to take a difficult road, sometimes an impossible road, or to take a road that's really easy. And once you see the solution is very logical and not much work actually goes into it, once you've sort of cracked the nut, so to speak. So what we're going to do this morning is we're going to cover a number of what I would consider to be important ratio problems. And they're going to be of varying difficulty. Some will be easy, some will be hard, just to kind of meet the needs of everybody here today. You're going to give them your best effort, and I'll probably give you at least 3 minutes on these guys, just because I want you to have the time to actually work on them and give them a good effort before we start. And I say this just about every week too, but it's because students always ask, what's the way to get faster at GMAT questions? And it's a great question, right? Because the test of time, then we all know we're shooting for about 2 minutes per question or so on the quant section. But the reality is there's just no magic pill. There's no panacea to get fast. So how do you get fast? You just get better. And that's the reality of the situation. And if I ask you guys what's 10 times 10, you'd all really quickly say 200. No, just kidding. You'd say 100, right? If I asked you what's a fourth times a fourth, you'd probably say 1/16th, but it would probably take you a fraction of a second longer. If I asked you what's 11/64 plus 14/97, now it's going to take you a little time. And why is that addition going to take you time? Well, it's going to take you time because you are not that skilled at adding difficult fractions. You can do it, right? I'm sure you'd be able to do it in 2 minutes. And then take something unusual like, what's the unit digit of like 7 to the 900th power? Well, the only reason why that takes anybody some time is they haven't been exposed to it, they haven't been used to it, they haven't been practicing with it. But even problems like, what's the unit digit of 7 to the 800th power or some other obscene exponent, they're easy to do as long as you know how to do them. So the key to getting faster is to practicing as much as possible, as good as possible, and just going crazy and really learning this stuff and making it your own. And that's how you get faster. So in the beginning, it's probably not the best policy to try and do questions within 2 minutes. And of course, the reason for that is you may just do nothing well. You may not get any faster, and you may not get any better. And then what would the point of that be, right? But at least if you are actually giving these problems a really good go, regardless of how long it takes you to start. Now, to be clear, I'm not saying you don't have to be fast by the end. But I'm saying if you give yourself the time to learn well in the beginning, you may just find that you miraculously get faster. And of course, it's no miracle. You're getting faster because you're getting better. So anyway, so that's why I'm going to give you more than 2 minutes. And we're actually going to start right now with this guy. And I'll be right here. I'll check back in a few minutes, and we'll talk about the answer. Okay, guys, that's about 3 minutes. So let's talk about this together. So remember, the key is going to be simplification here. So we have a jewelry dealer, and they purchased diamonds and emeralds but no other jewels. And it says the number of diamonds that she purchased was what fraction of the total number of jewels that she purchased. So here's the deal. Remember, in data sufficiency problems, we really want to do as much work as we can on with any given information. So what I would say is, let's simply say let x be the number of diamonds and y be the number of emeralds. Once we do that, we can really easily see that the fraction of the diamonds, so the number of diamonds that you purchased was what fraction. So what we're looking for is the number of diamonds over the total number. Right? We're looking for the number of diamonds over the total number of jewels. Right? So x plus y represents the total number of jewels. Okay, so statement 1, the number of diamonds she purchased was 7/3 of the number of emeralds she purchased. So we can say that x is 7/3 of y. We can say y is equal to 3/7 of x. And then a lot of beginning students look at this and say, well, it's not sufficient, right, because we have two variables in one equation. But they forget to see that we can use the given information with statement 1, right? And what we can do is we could substitute that in for y, right? So we'd have x over x plus 3/7 x. That would give us x over 10/7 x, or for the multiply, that will give us 7/10, which is obviously a set, consistent, unique value. So that does, in fact, answer the question. So we would say AD, BCE, because statement 1 alone works. That means the other two, B, C, and E have to be out, right? So statement 1 alone works. Either answer is A or the answer is D. Okay. Now, if we look to statement 2, it says she purchased a total of 150 jewels. Okay. Well, clearly that doesn't do anything for us here. But the trap, right, would be to assume that we need both 1 and 2 together. A lot of students will choose C for this question, when in reality the answer is A. So we didn't need to know she purchased a total of 150 jewels. But because in statement 1, we had the relative relationship between X and Y, and we were able to sub that in. Okay, so this is sort of an important ratio question. Yeah, it asks for what fraction, but at the end of the day, we're really simply dealing with a ratio. Okay, let's make this a little bit more challenging, actually a lot more challenging for some of you out there who have been studying for a while. The next one, it's going to seem a little difficult, but we're going to make it pretty easy. So let's definitely take about 3 minutes and work on this guy starting now. Okay, guys, let's take a look at that. That's a little over 3 minutes. Again, I want to make sure you have plenty of time to attack these guys. So what do we have here? So we have these robots in the lab, and the average age of a group of first generations is 35 months, and the average age of a group of second generations is 50 months. And if the average of all the robots is 40 months, what's the probability of randomly selecting a second generation robot from the pool? Okay, so there's a lot going on here, so I picked a problem that integrated a lot of topics, including a ratio. I'm not sure how the ratio comes up. So you guys got to remember that the average is equal to the sum divided by the number, and therefore the sum must be equal to the average times the number of numbers. So let's think about it. What's the sum of the ages of the first generation? Well, if we let f be the number of these first generation robots, and if we let s be the number of these second generation robots, then we can make it pretty easy on ourselves, right? We can say that 35 times f represents the number of first generations, right? Because the average times the number is the sum. Okay? And we can say that 50 times s represents the number of second generation robots, right? Because sum is average times number. And the sum of these two, well, they must sum, the sum of these two guys must sum to the total number of robots in the lab, right? Which is 40 times f plus s, right? And the reason why it's 40 times f plus s is the average age of both groups is 40, and the total number using our variables would be f plus s. Okay, so we'll say 35f plus 50s is equal to 40f plus 40s. Kind of combine all the like terms there. We'll see that 10s is equal to 5 times f. We'll say s over f is equal to 5 over 10, or s over f is equal to 1/2, and we may even say, well, f is equal to 2s. Both of these guys are saying the same thing here down here in the box. Now, if this is a data sufficiency question, a lot of students say it's insufficient, and because it's a problem-solving question, a lot of students don't get it right because they say, well, I don't know what to do from here. But if you think about it, what are they looking for? They're looking for the probability of randomly selecting a second-generation robot. Well, probability is just a ratio, right, of the favorable outcomes divided by the total outcomes. Okay? So what that means here is what are we looking for? Well, we're looking for s divided by 3s, right? S divided by 3s. Where's that coming from? Well, the original fraction would have been s divided by s plus f. All right? Oh, hold on, guys. I gotta mute somebody whose audio is coming through. Okay. Muted. Okay, cool. Right, so the probability we're looking for, I'm highlighting down the bottom right in this teal green box, would have been s over s plus f. That's a very simple ratio that we're looking for this probability equation. But because we know that f is equal to 2s, well, the denominator just becomes 3s. And we're left with s divided by 3s. And of course, this reduces simply down to 1/3. Okay, so the answer here is A. So I like doing problems like this because even though it's not a ratio in the most traditional sense, we got to weave a lot of stuff in here. We got to weave in the average formula, a nice word problem, probability, and the concept of the ratio. What I'm really trying to show you here, there's a lot of things I could show you, right? But what I'm trying to show you here is a lot of times, I look back at the last problem, we can express a ratio with variables of a part to total. It's a part to total ratio. And here, S over S plus F is a part to total ratio. And it's a valuable technique because it allows us to circumnavigate other issues that can arise if we can't do that. Okay, very good, very good. So I'm going to do one more challenging problem with you guys, and I'm going to turn it over to Jeff, who has a number of interesting problems to do with you. So we'll take about 2 to 3 minutes on this guy. It seems wordy, but it's not so long. Let's start on this now. Okay, guys, let's talk through this one. So Monday, this corporation, the ratio of number of employees who had meetings to those who did not was 2 to 3. I think half the battle is coming up with the variables that are easy to remember. So I don't know, let's say M is had the meetings on Monday, N is did not have the meetings on Monday. Okay? So if on Monday those who did to those who did not was 2 to 3, well, what we can say is M over M plus N is equal to, we may want to use ratio multipliers here. We may want to say 2x over 2x plus 3x, right? And again, the ratio multipliers there just remind us of the fact that we don't know exactly what the numbers were. We know it was 2x to 3x, okay, which is important. So from here we can say this is 2x over 5x. Well, we can say this is 2 to 5. Now, you didn't have to use the x in there. If that was confusing to you, you don't have to use it. You still got 2 to 5. I was just adding in the ratio multipliers there, so we would all be sure we didn't actually know what the numbers were. We just knew that we were dealing with a ratio. Okay, so 2 to 5. And then on Tuesday, the ratio of employees who did not have was 3 to 4. So again, I don't know, let's say P is the number who had on Tuesday, S is the number who did not have on So what we're looking for is T over T plus S, and We'll toss in another ratio multiplier. Never use the same ratio multiplier unless you know for sure it's the same. Again, what I do here, I just use the y to represent the fact that we have a ratio. We don't know for sure if it's 3 and 4, it could be 30 and 40, etc., right? So here we can see this goes to 3y over 7y, which is 3 to 7. Okay, here's where the real magic comes in. Most students get stuck here, but I want you to think about this. If we have one that's a ratio of 2 to 5, right, and we have another that's a ratio of 3 to 7, well, what's the only way that could be? Well, we need a total number of employees. We need a total number of employees that's divisible by 5 and divisible by 7, right? Because we can't have a fractional number of employees. And the only number here that's a multiple of 5 and a multiple of 7 is 35. So 35 is the answer. So guys, remember this. This is sort of the last important parting tip I can give you. Definition of insanity is doing the same thing again and again and expecting different results. So some of you here, I don't know. If you're using our stuff, you know you have a competitive advantage. If you're using other people's stuff and you like it, by all means, continue using it. But if you're using other things and you're not getting the results you want, just remember the definition of insanity is doing the same thing again and again and expecting a different outcome. So you may consider swapping up the way you're preparing. Time is valuable, and time is definitely of the essence of the Gmat. So with that said, I'm going to turn this over to Jeff, who, as I said, has a number of interesting problems planned for you, and I'll look forward to talking to you soon.
Hey everybody, thanks for coming today. So Scott did some great stuff with you, and yes, I concur with him that people have been doing some amazing things with our curriculum, so certainly there's no reason why anyone here can't. It's actually astonishing how well people have been able to do on the quant section. So hopefully most of you are using our stuff here. So what I want to get to here today is something we talk a lot about in our ratio chapter, about what actually makes a ratio. And I find that to be a really cool topic because the interesting thing about ratios is they're kind of sisters to fractions and also percents. So like, for instance, if you can determine the ratio of something, you can determine the percentage of something or a fraction of something. And to even expand on that just a little bit more, I mean, 4/5, it's a fraction, right? But it's also a ratio, but it can also be a percent if you divide 4 by 5 by 100. And of course, that ultimately ends up being 80%. Divide 4 by 5 and multiply it by 100. So on the Gmat, you can get asked different things, especially in data sufficiency, and it doesn't matter if they're saying, what is the ratio of, what is the fraction of, this is a percentage, what is the percent of. It's all the same stuff. So if you know how to do it in one direction, you know how to do it in many other directions. So we are going to talk a lot about that today, and hopefully by the end of this, you will be extremely familiar with this concept or this idea. So the first one I want to do with you is a pretty basic ratio question, and give everyone about 2 to 3 minutes, and then we can go from there. Okay, that was about 2 minutes there. So this is an interesting question because there are different ways you can deal with it. I like to set up using variables, and then I like to set up making equations. I feel like there is a word translation involved in here that we can take a look at. So the first thing I would say is we have two equations. And the first thing that's said is that 1/2 of the convertibles are equal to 1/5 of the total. So we can say 1/2 C equals 1/5 total. And then it says, and 1/4 of the sports cars, which we'll call S, is equal to 1/8 of the total. Now, the next thing we'll notice is it says what is the ratio of convertibles to sports cars. So we would say C over S equals what? From there, we want to try to get everything in terms of the same variable, meaning we want to get C in terms of T and S in terms of T. The reason we want to do that is because if we sub those into the ratio, our T variables will just drop. So let's do that right now. What we can do is we can multiply everything on the top by 2, giving us C is 2/5 T. On the bottom, we can multiply everything by 4, giving us S is 4/8 T, or in other words, S is 1/2 T. Now, we take this, we sub in for C, we take this, we sub that in for S. Now, this is the beauty of this, is all of this stuff is going to cancel itself right out once we sub in. So we have 2/5 T on the top, we have 1/2 T on the bottom. Notice the T's drop, and then we just flip and multiply, and you get 4/5. Now, some of you may have done this problem a different way. I will tell you there are multiple ways to deal with something like this, and it's not to say that your way is the wrong way. Some people like to sub in when they're dealing with ratios, or excuse me, when the answer choices are in ratio form. And I'm not saying that's wrong, but I am saying that is slightly different from something I did. At a bare minimum, I think setting up the equation is very important because that equation that I made right off the bat is what allowed us to kind of relate all the variables to each other. So even if you're subbing, I would recommend you doing that. So what I want to do is I want to take this idea and I want to apply it to data sufficiency actually. And I want to go through some very specific skills that they can test you on in data sufficiency. And then I kind of want to relate it back to a few of the things that we talked about earlier with percentages and fractions. So why doesn't everyone give this a shot here? Okay, so that was about 2 minutes there, 2 to 3 minutes. And this is a very good question because this is testing you on the idea of how to set up and create a ratio. So here's the interesting thing. We have dollars per case of white wine. We have dollars of case per red wine. But here's the deal. They want revenue. So anytime you see that you're dealing with revenue on the Gmat, there is a high likely that you need a quantity and a price per item. So what I do right off the bat is I have red and I have white. And I say, okay, I'm going to use I'm going to use two variables they gave me. So R is dollars per case. And X is going to be quantity of cases. So we'll just do that for short. W is dollars per white. Y is quantity. Now, what does that mean? Well, if it says what's the ratio, the revenue of ratio from red to white, we have Rx over WY is equal to what? Okay. So the goal is what we did in the last question. Nothing has really changed here. We need to get everything in terms of the same variable, see if the variables will drop. Now, there is one piece of good news here, and that's that this is what I call a 50-50 question. The answer is not going to be A, it's not going to be B, certainly it's not going to be D, so it's either going to be C or E. It means that when you guess, you have a 50-50 shot. Doesn't mean it makes it easier to get the right answer, but it does eliminate some of the possibilities. The reason I say that is because statement 1 only refers to the number of cases of red, and statement 2 only refers, the number of cases in general, and statement 2 refers to the dollar amount for the cases. So what we're going to do is two quick word translations, understanding that statement 1 and statement 2 are not going to work. And the first thing is we are going to do the translation for statement 1. 4 times as many cases is red as white, so we're going to say R equals 4W, or excuse me, not 4W, X equals 4Y, because it's saying there's 4 times as many cases sold as red. And then statement 2, each case of white, 50 more than each case of red. So we are going to follow the same approach as before. X equals 4Y. We're going to go ahead and sub that into X. W is R plus 50, and we're going to sub that in. So we have R 4Y over R plus 50 times Y. And this is where you have to be so careful. The Y's drop, and we're left with 4R over R plus 50. Now, that's not a ratio, because the R's don't cancel, and depending on what R is, it changes what the ratio is of revenue from red to revenue of white. Thus, the answer here is E. Now, we are going to do a problem that's similar to this, and then we're going to kind of talk about the overall idea of what we just did here, and then we can kind of go from there. So let's talk about question here. You're going to think it's the same question, but I promise you it's a little different. And I'll give everyone about 3 minutes to work through this, and then we'll talk about it. Okay, so it's another 2 to 3 minutes. So this is an interesting question here because it is extremely similar to the last question with some slight differences. The difference really is statement 2. In statement 2, we have them selling 2 times as many cases of white as it is red. Notice in the last problem we were dealing with addition. So what we have here, and we're going to set up this the same way, we have our red wine. We're going to call R equals the dollars per case. We're going to call X equal the number of cases. We're going to have white be the dollars per case. And let me make that look more like an X, and Y be the number of cases. So again, what's the ratio of red to white? Rx over Wy is equal to what? So let's set up our equations. Again, this is still a 50-50 question, so we'll take that approach. Last Sunday, they sold 3 times. They sold each case of red, so this is a price equation for 3 times as much as each case of white. So we would say R equals 3W. And then we'd say last Sunday, they sold 2 times as many cases of white, so Y equals 2X. Now, the final step, which we did before, we take this, we sub that in for R, we take this, we sub that in for Y, we end up with 3WX over 2WX, and we cancel out, and look at that. We get a ratio of 3 over 2. It's sufficient. Now, some of these principles you can take to the bank in the sense that if you see a problem like this, look out for these things. Now, they can ask problems in different ways. But if you see a revenue-based problem and you notice that there's going to be 4 variables and you notice one statement is giving you an addition or subtraction relationship and the other one's giving you a multiplication relationship, it's probably going to be E. And if you have a similar problem where you have 2 multiplication relationships, it's probably going to be C. Now, yes, they can throw in different things, so I can't say for sure that that's how this is going to work out, but at least you go into the problem with an inkling of what to expect. So with that said, the other thing I wanted to kind of wrap up with is that this problem could be a percentage question. They could have easily said the red revenue is what percent of the white wine revenue. That's C. They could have said the red revenue is what percent greater than the white revenue. Again, it works. They could have said what the white revenue is what percent less than the red revenue. It works. They could have said the red revenue is what fraction of the white revenue, and it works. And finally, they could have also said, what is the percent change between the red revenue and the white revenue? This is crazy because all of those work and ask the same darn thing in a different way. So if you're on the Gmat and you see any combination of what I just asked, you want to be taking the approach that we just took here. Can I plug in and get all my variables to drop? And can I be left with just a ratio? So hopefully between what Scott did and I today and what everyone did here today, you're really taking in some really great principles about ratios and fractions and percents. As always, we thank everyone for coming. We hope we got a lot of good stuff done. We hope you learned a lot. And we'll be here next week. So hopefully everyone can come over. And as Scott said, if you're not using our curriculum, I'm telling you, you're missing out. So at least try it, and we'll talk to you soon. Thanks again, everyone.